Question 4. A uniform rod AB has mass m and length 2a. A particle of mass 2m is attached to the rod at the point C, where AC is 1.5a. The rod rests with its end A on rough horizontal ground. The rod is held in equilibrium at an angle of theta to the ground by a light string that is attached to the end B of the rod. The string is perpendicular to the rod as shown in figure 2. Explain why the frictional force acting on the rod A acts horizontally to the right on the diagram. Okay, well, we have a diagram, figure 2. Let's start labeling forces. So we've got the uniform rod. Uniform means that the mass of this rod is going to be acting in the center. So as it's got a length of 2a, that is A from A, so half of 2a. And its weight is its mass times the acceleration due to gravity, which is g. So we have mg, force acting down. This weight has two components, one acting perpendicular to the rod and one acting parallel to the rod. The particle of mass 2m is at the point C, which is 1.5a. The mass of 2m, so we have a weight of 2mg, this time acting horizontally down. And this also has two components acting perpendicular and parallel to the rod. The rod is resting at A, so there is a reaction force on the rod from the ground at A. We're told that our friction at this point is acting to the right. We need to explain why. Typically, to stop a rod from sliding, we would expect the friction to act against it, and so in this case it would be acting to the right. The string over here is perpendicular to the rod, so we have a T, a tension in our string, and that tension has two components of forces, one acting vertically up and one horizontally to the left. Why then should this frictional force be acting to the right? Well, I've said we don't want the rod slipping, but equally, if we look at the diagram, if we consider forces to the left and right on this diagram, the only force moving to the left, we have this component of tension in the string, but there is nothing to counter it acting to the right, and so our friction must be acting to the right. If friction acted to the left, there would be no forces acting to the right, and therefore there would be no equilibrium in this case. The tension in the string is T. Show that T is equal to 2mg cos theta. Let's take moments about A. So remember, moments are the perpendicular force multiplied by the distance. And typically, because this is in equilibrium, we're going to label clockwise forces equal to the anti-clockwise forces. So the forces we've got acting on this rod anti-clockwise are the T is acting anti-clockwise, and that is a distance of 2a from A. So 2at is the anti-clockwise force. Our two clockwise forces come from the weight at C, and it's this component, so that would be 2mg cos theta, and that's multiplied by 1.5a, which is the distance. And we have the weight of the rod, mg, which is a distance of A. So mg cos theta is the component perpendicular to the rod, and that's multiplied by A. So A mg cos theta. If we simplify this, 2 times 1.5 is 3, add the other 1, we've got that 2at is equal to 4a mg cos theta. And divide both sides by 2a to leave us with t is equal to 2mg cos theta, which is what we wanted to show. Part C, we're given that cos theta is equal to 3/5. Now, because cos theta is equal to 3/5, this is an example of our mechanics questions giving us a nice Pythagorean triple. Remember, cos is adjacent over hypotenuse, and if you have a 3, 4, 5 triangle, then the remaining trig angles, we have sine theta is 4/5 opposite over hypotenuse, and tan theta is opposite over adjacent, so 4/3. These values can also be found on your calculator if you don't remember your triples. Show that the magnitude of the vertical force exerted by the ground on the rod at A is 57 mg over 25. So that's this force here, this R. We want to show that R is equal to 57 mg over 25. So let's look up and down then, since R is working upwards. Then the upwards forces are R plus T cos theta, this component from the tension in the string, and that equals the forces acting downwards, which are the two weights, mg and 2mg, so 3mg acting downwards. We've found T already to be 2mg cos theta, and so we can substitute tmg cos theta in for T to give us r plus 2mg cos squared theta is equal to 3mg. Cos theta we know to be 3/5, so we can substitute for that, giving us r plus 18/25 mg is equal to 3mg. Subtracting 18/25 mg from both sides gives us that r is equal to 57 mg over 25, which is what we wanted to show. The coefficient of friction between the rod and the ground is mu. So let's pop mu on our diagram. Given that the rod is in limiting equilibrium, show that mu is equal to 8/19. Let's look left and right. And so we know that our force acting to the right, which is friction, is equal to our only force acting to the left, which is this component of tension in the string. So that's T sine theta. We know T to be 2mg cos theta, so we can substitute that in, giving us friction is equal to 2mg sine theta cos theta. And we know sine theta and cos theta to be 3/5 and 4/5, which gives us a value of friction of 24/25 mg. Now, our other formula for friction is that friction at limiting equilibrium is equal to mu r, and we are in limiting equilibrium. Now we can say friction is equal to mu times the value of r that we've found to be previously 57 mg over 25. And given I have two equations for friction, I can put them equal to each other. So mu 57/25 mg is equal to 24/25 mg. And so dividing both sides by 57/25 mg does give us a value of 8/19 for mu.